This is section 4.6, Model Direct Variation. Two variables, x and y, show direct variation provided y equals ax, where a is not 0. The non-zero number a is called the constant of variation. So we would say y varies directly with x. Notice, y equals ax is a linear equation that is in slope-intercept form, where m equals a and b equals 0. So the graph of a direct variation equation, because remember, this is the same thing as slope-intercept form, except there's an implied plus 0. So if the b, or the y-intercept, is 0, well, that means that it has to go through the y-axis at 0. Well, if it goes through the y-axis at 0, that means it also has to go through the x-axis at 0. So you know you can put a point at the origin, and then 2/3 is still my slope. So that's why you go up 2 and to the right 3 for a second point. But direct variation equations must go through the origin. So again, the graph of a direct variation equation is a line through the origin, and the slope of the graph is a. So y equals ax, we say that instead of having to say y equals mx plus b, where b is 0. So with direct variation, it's understood that it's of the form y equals ax. So if the slope a is positive, then obviously it's sloping up, and if the slope is negative, then it's sloping down. But no matter what, the graph must be going through the origin. Okay, so one thing you have to be able to do is recognize whether an equation represents direct variation or not. So looking at this example, because x and y are on the same side of the equal sign, we can't really tell until we solve for y. So again, going back to our literal equations, just like we did before, we want to get y by itself. So before we can do that, we need to move that 2x over. And again, it is a positive 2x, so to move the whole thing, I need to do minus 2x from both sides. So I'm left with negative 3y equals negative 2x, and that's important. That negative doesn't go away just because the 2x moved. And then to get y by itself, I need to divide by negative 3 because it's being multiplied by y. But whatever I do to one side, I have to do the other. So now y equals, well, a negative divided by a negative is actually a positive, so I'm left with 2/3 x, or 2x over 3. Now you have to ask yourself, is that in the form y equals ax? Well, because there is no plus b here, yes, it is of the form y equals ax, where a is equal to 2/3. So we would say our constant of variation is positive 2/3. And here's another example. Again, negative x plus y on one side makes it a little hard to tell, so we need to move that negative x over. Because it's negative, we're going to add x to both sides, and we're left with y equals x plus 4, or 4 plus x. And again, we need to ask ourselves, is that of the form y equals ax? Well, no, because plus 4 means that it's going through the y-axis at a positive 4, which means it's not going through the origin. So if it has a plus b at all, it cannot be direct variation. Because remember, direct variation has a plus 0 that's implied, because the y-intercept is 0 because it's going through the origin. Okay, so we can also write a direct variation equation using a graph. So again, notice it's going through the origin, so we know it's not going to have a plus b, So we know it has to be of the form y equals ax. We just have to find a. So because we have this point at -1, 2, we can find the slope by counting. Remember, that origin that it's going through, that's another point. So our slope is rise over run. Our rise, we could count down to -2 over our run, +1, which is equal to -2. Or we could go the other way. We could start at the origin, count up to +2 in the rise, and to the left one is -1 in the run. Well, that's still -2. So our direct variation equation would be y equals -2x. Now the second part says find the value of y when x is 30. So all we have to do is now use our direct variation equation and plug in 30 for x. So y equals -2 times 30. Well, -2 times 30 is -60. Okay, so direct variation applies to a lot of real-world situations. So we will give you a situation and ask you to set up the direct variation equation. So we have a saltwater aquarium. The number S of tablespoons of sea salt needed in a saltwater fish tank varies directly with the number W of gallons of water in the tank. Okay, the first thing you need to notice there is that it says varies directly. If you see that, that means that you are setting up an equation of the form y equals ax. Except in this case we have S and W. So the number S tablespoons of sea salt varies directly with the number W of gallons of water. In this case, our y and our x are actually S and W. So we have S, the amount of sea salt, is equal to the constant of variation times W, the amount of water. So it then goes on to say a pet shop owner recommends adding 100 tablespoons of sea salt to a 20-gallon tank. So we can use that to help us find the constant of variation. So we have 100 equals A times 20. Because 20 is our amount of water and 100 is our tablespoons of salt. So now we can solve for A. Well, because 20 is being multiplied by A, we're going to divide by 20 on both sides. 100 divided by 20 is 5. So we know our constant of variation is 5. So we can write a general equation to relate the amount of salt with the amount of water. So we say S equals 5W. And now we can use that equation to answer the next part of the question. So again, S equals 5W. And we want to know how many tablespoons of salt should be added to a 30-gallon saltwater fish tank. So, since we know S and W vary directly, we can plug 30 into our equation and figure out how many tablespoons of salt. So, our salt is equal to 5 times 30. Well, 5 times 30 is 150. So we know in a 30-gallon saltwater fish tank, we would need 150 tablespoons of salt. And that's it for the section.